Hello, this is Dr. Lori. Welcome to this video discussing causation. So before we begin, I would like to go back and think about some of the things that we've learned in the past about looking at relationships. So specifically, when we're evaluating a relationship between two or more variables, we do that so that we can come to some kind of a conclusion. When I come to a conclusion, I could be wrong. That's called error. I could make the wrong conclusion, or I could be right. And if I'm looking at relationships, if I'm right, that means that there is some kind of an association between those two variables. I can be wrong for a couple of reasons. I can be wrong by chance. In other words, that sort of random error, that wrongness could be in either direction, kind of randomly, or I could be wrong systematically. Bias is this systematic or differential error, and bias tends to be being wrong in a specific direction. So we'll be talking more about that later, but I want to focus right now on what if I'm right? What if I come to this conclusion and there is an association? There are a couple of different reasons that there could be an association. It could either be causal or it could be what's called non-causal. So, and we first would need to sort of define this idea of causal. The best way that I've thought of to explain this idea of causal is if a risk factor or a variable of some kind causes a disease or a specific outcome, if I were to take that risk factor away, then the outcome also disappears. So, in this sense, if I were to say if X leads to Y, if I was to get rid of X, then I would no longer have that particular outcome happening anymore. And so now we need to kind of diverge for a couple of minutes into the whole terminology that epidemiologists use for causal. Sufficient cause means that that particular risk factor or variable was sufficient enough to cause that disease. In other words, every single time that particular risk factor is present, the disease happens. So let me clean this up just a little bit. I need to get rid of all the scribbles. If X leads to Y and it's sufficient, then that means every time X is present, then Y will be present. Now, you'd think that this happens all the time, but actually it's pretty rare. So we have a couple of examples of sufficient cause. If we have a specific genetic disease, say Down syndrome or sickle cell anemia, and we have the genes that cause that disease, by definition, having the genes means that the disease is always present. There are certain severe injuries that can happen that always lead to death, for example. And so then that particular risk factor or exposure or event would be considered a sufficient cause. Again, it's pretty rare. A lot of times people will say, well, smoking causes lung cancer. Well, it's not a sufficient cause because some people smoke and don't have lung cancer. So smoking all by itself is not sufficient to cause that particular outcome. And we'll talk a little bit more about that coming up. The next thing is necessary cause, and you can just kind of like plug that word in. A necessary cause is necessary to be present for that particular disease or outcome to occur. And this happens a lot in public health, specifically with infectious diseases. In order for a person to have tuberculosis, either latent TB or active TB, they must be exposed to the tuberculosis organism. no matter how suppressed your immune system or how terrible everything else is happening around you, poverty, crowding, those kinds of things, unless you have the tuberculosis organism present, you cannot have TB. So that's a necessary cause. Infectious disease is a really common example of necessary cause. So it has to be a part of what's causing this particular outcome to happen. Now, like I said, there are very few sufficient causes where that particular thing is sufficient all by itself. And so Rothman, a prominent epidemiologist in the United States, has actually come up with a something called a sufficient cause model. You're going to hear it called other things. You'll hear it's called sufficient component cause. You'll hear them called causal pies. But the basic idea, so I'm going to put that here, sufficient cause model. The reason that this is so important, and this is really, really key to understanding association and causation for the entire quarter. So this is really a key. We'll be talking about this more. Is for each individual, there's very likely a collection of factors that together, when they all happen at the same time, that collection is sufficient to lead to that particular outcome or disease. And so if we had perfect knowledge and A, B, C, and D were all present for a particular person, then that is sufficient to cause that particular disease or outcome. And every single time those four factors are collected together, then we always have the outcome. That's the definition of sufficient cause, is that when that particular cause is present, the disease will always occur. So it's sufficient to cause the model. Now, we don't have perfect knowledge. There are a lot of variables we either don't know about or can't measure. But for example, let's think about that whole thing with smoking and lung cancer. If a person is a smoker, then that would be one thing that increases their chances. Let's call A is smoking. Maybe there are certain genetic predispositions to lung cancer. Perhaps a person, for some other reason, their immune system isn't active enough to kind of contain or capture those early cancer cells. There could be some other environmental exposure that a person had at a specific key time, either fetal development or during a specific time during childhood when the lungs are developing, that they had this particular environmental exposure. So every single time we have that particular combination, smoking, that particular genetic thing, that particular immunity level, that particular environmental exposure, then that would be sufficient to cause lung cancer or cause that outcome. Now, smoking is not a necessary cause for lung cancer because some people get lung cancer who are not smokers or not even exposed to environmental tobacco smoke. Before smoking was invented, we had lung cancer before that. And so smoking is not required. So basically what that tells us is that other people who end up with lung cancer might have a different causal pie. Maybe they aren't smokers, but they still have B, C, and D, but maybe they also have E and F. They have some other factors that are contributing to this causal pie. Now remember, it's the collection, it's this combination that when present will always cause the disease outcome. If I was able to get rid of F and B, C, D, and E collectively together would cause lung cancer, then F was not part of the sufficient cause. If I need F, if I get rid of F and it was part legitimately part of my sufficient cause model, then B, C, D, and E by themselves would not lead to that particular outcome. That person would not develop lung cancer. And so you can kind of see where I'm going. If I can remove any one of these, let's say I can remove E, F, B, C, and D together are not enough to cause lung cancer by themselves. So when we think about the definition of causal, if we were to remove that cause, then the outcome will not occur. I'm going to get rid of my scribbling just because I need those later. If it's a sufficient cause model, if I can get rid of any one of the pieces of the pie, then my outcome will not occur. Another important thing then to realize is that with this sufficient cause model, different people have their own pie. And so let's say for me, in order for me to get lung cancer, I would have to be a smoker. Let's just imagine that that would be the scenario. Since I'm not a smoker, I would never get lung cancer. But maybe my sibling has a different sufficient cause model, and they could theoretically get lung cancer without ever being a smoker. Each person then has their own pie, and multiple people could share the same pie. It could be that people have F, B, C, and D, and that comes together and it causes the particular outcome. It's probably much more likely that these sufficient cause models have dozens, if not more, little slices in them in order to lead to that particular outcome. We don't have perfect knowledge. If we had perfect knowledge, we would know what all of those pieces are and we could measure them. And as soon as we take one of them away, then that particular outcome for that person would not happen. Now I want to present you with a puzzle. I heard this at a convention and I thought it was quite clever because it has everything to do with this whole notion of the sufficient cause model, where we have multiple things causing a specific outcome. The speaker got up and they said, what percentage of disease do you think is caused by genetics? And he said, we've actually done quite a thorough review of just sort of diseases in general, and we found genetics cause 90% of disease. Keyword here is cause. And then so what percentage do you suppose is caused by environmental? And I'm using environmental very, very broadly. This is the question of nature versus nurture. In other words, you have this genetic predisposition that's all inside of you, inside of each cell that you have, and environmental is everything that happens to you from the outside. It could be the food you eat, it could be environmental exposures, just particular toxins, but it could be even the way you were raised, the things you were taught as you were growing up, every possible external influence on you. What percent is environmental? And the answer is 90%. And someone will say, how can that possibly be? 90 plus 90 is more than 100%. And here's the reason for that, is because the definition of causal means that it is a piece of the sufficient cause pie, of the causal pie. If I were to take away all environmental causes of disease, I would get rid of 90% of disease. Because it's a big enough piece of the pie, it's a piece of 90% of people's pies, where if I got rid of it, then the outcome would no longer occur. Remember, if I get rid of the exposure, I get rid of the outcome. Genetics, same thing. It is a piece of 90% of the pies. And so, by definition, if I got rid of all of the genetic issues that contributed to diseases happening, I could get rid of that as a piece of the causal pie. I could get rid of 90% of diseases that occur. And so when we try to say, well, this percent of cardiovascular disease is caused by your diet, and this percent of cardiovascular disease is caused by your BMI. This percent of cardiovascular disease is caused by smoking. This percent of cardiovascular disease is caused by your genetics. We're trying to have those add up to 100%, and it's artificial because for any given person, they could have all of those things be part of their sufficient cause model. If they were to take any one of them out, if they truly were a part of the sufficient cause model, then that particular outcome would not occur. Remember the definition of sufficient cause. If the cause is present, the disease will always occur. So, because it's a complex collection of things that cause a specific outcome, and often collectively together, we'll see in a minute, then this whole notion of causality becomes really, really complicated really fast. So that's a summary of this whole notion here of causality. Probably the one thing that I should add to that will be helpful is that causation can be both direct and indirect, and that can be kind of confusing. Here, let me actually get rid of some of this here so I can put those in. Let's say causation can be indirect and direct. Remember, by causal, we mean that if you took away that risk factor, each one of these is a risk factor. Anything that increases the probability of disease. If we took away that particular causal mechanism, that the disease would also go down. Indirect means that there are intermediary or intervening factors before you get to the disease. I'll put those intermediary and then disease. And with direct, you have that particular exposure and it goes directly to disease. People struggle with this concept quite a bit because they can say, well, I eat a specific food and it causes a cascade of biological and chemical reactions inside of my body, and so that must be indirect. The way I like to think about indirect versus direct is that indirect, these intervening factors are things that are external to a person. So in other words, a really good example of an indirect risk factor for particular outcomes is poverty. Not having money in your pocket doesn't directly cause you to have disease, but it indirectly means that you may not have the money to buy nutritious food, you may not be able to go to the doctor, you may not have access to certain things because of poverty. That increases the chances of having a particular disease. And so poverty is a great example of an indirectly causal. If I took the poverty away, if suddenly you did have money, it's not the money that fixes it, but the money gets you the things that fix it. And so that's that indirectness of it. If I could get you all of those things without taking away the poverty, then I could also get rid of the disease. So I can have an impact in a variety of ways. Some people would say that if I get rid of those intervening factors, I have in fact gotten rid of the poverty. So it becomes much more complicated right away. Directly means if you eat a certain diet, your chances of having certain diseases actually goes up. The food goes into your body, and sure, it's processed and different biochemical pathways happen as a result of that. Maybe you get atherosclerosis, or you have a variety of different things happen internally to you. But that's all happening inside of your body, and so that's considered to be a direct cause. If I took that particular dietary pattern away, then the disease, that's the outcome, would actually also change. So being indirect or directly causal is a kind of distinction that we make. although a lot of times in the literature it doesn't matter so much. I like to think of causality as being really this web, this interaction between a variety of different things. They're all influencing each other. Sometimes even there's this relationship between two of the variables that if one is present, it actually also causes the other one to get worse. And so there's this complicated mechanism that's really ultimately leading to that particular disease outcome. So thank you so much for joining me, and we'll have another video really looking at association versus causation.